So now this is okay. So this this number has changed. I think so. This number used. I don't know what's going on. Something's changed, but it's about a gigabyte a second. So I think we all agree that if you have a single process writing to a single file, it used to be a bit more than a gigabyte. Now it's a bit less than a gigabyte. This is old data. Multiple processes. This is coming back to Luis's said. Yeah. So as Luis said, a single serial process limited about just under a gigabyte per second. If we run a node is limited to 50 gigabytes a second. Now that is, Luis said that's more severe bottleneck than the disk. It's more of a severe bottleneck than the file system. But remember, this benchmark, with the proc benchmark, is writing lots of files, but they will be distributed across the OSTs. So you're actually stressing the entire file system here. So does that make sense, Luis? So it's a more severe bottleneck than the file system. A single OST is about 10 gigabytes. That's more difficult to measure, but yes, file system. A single OST is about 10 gigabytes. That's harder to measure. You can do it, but so that's right. Now, Luis makes a very right. So, any reason why striped is slower than unstriped? So, yes. So when you do unstriped, yeah, with node equals 2 task equals 1 to 8, you're writing 256. You're writing 256 files. So let's just and there's 12 OSTs. So you're writing. Let's assume they're distributed. Now remember, even though you're doing serial I/O, because you're doing lots of them, you're using the parallelism of the file system. And so for node equals 2 task equals 1 to 8, you've got 256 files, which are being spread over 12. So you've got about 20 files per OST. So each OST has to cope with 20 writes going on at the same time, 20 files being written to it. Okay. So there's no need to stripe because you're already saturating the disks because you're writing lots of serial. If you stripe, each of those files is across 12 disks. So each disk OST is then coping with 12 times as many. Each disk is then coping with 256 files. So you've got, do you see what I mean? So you've got, if you don't stripe, each OST has to cope with 20 large files. If you do stripe, each OST has to cope with 256 small files, each of which is a slice of the original file. Does that make sense, Lewis, sorry. Yes, so it's actually a very good point. You do not want to stripe. You want to write to all the disks. If you're writing lots of serial files, you're already doing that, and striping each of those just overloads it. So, but that's a very good point. What were the numbers? You said it was slower. I'd just be interested in did you get a sort of ballpark for what the numbers were? For what the sort of numbers were. Okay, fine. So that's, yeah. So you're getting a sort of 50% content. That doesn't make sense. The reason I don't want you to do all these runs is that if you run all these big ones, then the system you'll crash the file system. Well, you won't crash it, but I think so this number, the single process number is. I don't understand why I used to get 1.2, and this is something we need to take up with HPE. There's been some change in the configuration I don't understand. It could be a Fortran issue. Maybe I don't know. I don't know if it's a Fortran issue or if it's a C issue. But the important point is that it's about a gigabyte per second. So I know it's about 50 gigabytes per second. The file system is actually about 100 gigabytes per second. That's the disk file system. Actually, the NVMe is much higher. The NVMe, I should have that here, but because I didn't. The NVMe is about. I'll type in. So the NVMe is potentially huge. It's got, but each OST is quicker, and there's more of them. So that's about, you know, the NVMe potentially has huge amounts of bandwidth available, but it's quite hard to get. Okay, so that was very interesting result. So hopefully, the way you've run the benchmark there, all it does is it's a program that does it does open, write, close, literally. But even with a really simple program like that, you can start to understand where the bottlenecks are and what doesn't work on a parallel file system. So that's why I find that useful. Now I'll just the next lecture. Take me a second to. So what I wanted to do was to give you a sort of a brief overview of how MPI-IO works, but I'm really using it as a kind of a generic model for how all parallel I/O works. But I will go through MPI-IO in not enough detail, just in detail to explain how it works. I'm not going to actually cover how to do it at the very detailed level, but I'll cover the basic steps and hopefully explain. Okay, so I'm just checking I'm recording. Okay, I'm recording. Is this the next lecture? Okay. So what I'll cover is the MPI-IO model, which I briefly sort of at least outlined before, the basic file handling routines, and something called setting the file view, which is MPI-IO's terminology for how each process tells the I/O system which subset of the main file it owns. And then really it's achieving performance, which is the thing that I'm most concerned about here. So just to recap, controller I/O, which I call serial in my benchmark, somewhat confusingly, apologies, use a single process for read and write. This requires a buffer to hold the entire file on the controller. That's not scalable to many processes due to memory limits. Okay. The MPI-IO model is the standard model for parallel I/O. Each process describes what subsections of the file it owns. I say subsections because in general they're non-contiguous sections. How do we do that? We use a standard MPI data types. And I'm not going to cover that in detail here, but if you're aware of MPI data types, in 2D, vectors allow you to specify strided data types. In multiple higher dimensions, you want to use MPI subarrays. But anyway, these are part of the I/O routines. Then the data is automatically read and transferred directly to the local memory. There's no explicit controller process, okay? I mean, so the MPI-IO model is a symmetric model. Every process, under the hood, there may be special processes, but at least from the user level, it's a complete symmetric model. Everyone just, yeah, there's no explicit controller. So the MPI-IO approach is there are 4 stages. You open the file, you set the file view, you read or write data, and you close the file. Now, of course, opening file, reading or writing, and closing is what you always have to do. All the complexity is hidden in setting the file view, and this is where the derived data types appear. And I'll very briefly show in the final lecture how other I/O libraries treat this data. Now, I am here always talking about in the back of my mind this very simple example of a 2D array decomposed across a 2D grid of processes, or for bench I/O, a 3D array across 3D grid. You know, more general unstructured problems you can deal with. It's just a matter of the set the file view, the telling the system which subsets the global data you and are more complicated, but in principle it's the same. Now, I've got here write is probably more important in practice than read. So actually, this is a hangover from the previous. In my MPI-IO examples, I used read because it made a simpler exercise. But actually, bench I/O does write. Sorry, this is a slight hangover. Why is write more important in practice than read? Because you know most parallel programs. Think about doing a weather forecast. You read in the weather today, and then you run for a day and dump the weather every hour. You typically computational science HPC programs typically write more data than they read. Now, for data science, it's probably the opposite, actually. They probably read more data than they write, because you analyze huge amounts of data and come out with a small answer. But for computational science, you typically write a typical figure is like an order of magnitude more data than you read. So writing is the thing that you're really concerned about, and that's why Bench IO does writing. This is this is a hangover from the previous course where these exercises, which were standalone MPI-IO exercises, used to read. But I will use read. Okay, so opening a file, MPI file open. It's just like a normal file, and just a normal open. You pass a communicator like you do to all MPI routines. You give a file name, and then you get back a file handle. So this is just like your unit number or your file pointer in C. You give an access mode, which is normal. Do you want to do, read only, write, write only? There's some various constants to help you with that. And there's an info, which is a bunch of extra information. And in principle, in that info object, you can specify things like the striping of the file. So, I mean, but in practice, I find it not useful to do that. I tend to write my MPI-IO with this set to MPI info null. These are hints, basically. These are IO hints, which you can pass. But I find it much easier to leave that blank and optimize IO by doing by configuring Lustre, for example. But this is, I mean, MPI file open attach the file to the file handle. You use this handle in all the future IO calls, and it's analogous to C file pointer or Fortran unit number. It's collected across the communicator, MPI com world if you want, and the access mode is a bunch of these funny constants: create, read only, write only, whatever. So examples, and I'll do the C one here. No, MPI file handle, access mode is MPI read. I'm doing a read here, read only. MPI file open, MPI com world, data.in. Access mode is read only. I do MPI info null because I'm not passing any hints, and I get back the file handle. It's the same with Fortran, except these things are integers in the normal way. Just a slight technicality, you must specify create as well as write for new files. So you have to or add the access modes together. It's a slight weirdness. Closing a file, you MPI file close. Big deal. Collect across the communicator. So you've got MPI, but if now I've got read here, but if you Bench IO does write actually, but it's completely symmetrical. You MPI file read all, MPI file write all. You pass the file handle you previously pointed, and this is a bit like a read is like the way the MPI-IO works is a read is like a receive from a file, and a write is like a send to a file. So this looks like a read or a write, a send or a receive. You MPI file read all, MPI file write all, the file handle, the buffer, count data types, and then you get back a status, which gives you some information on what happened. And so an MPI file write would do the opposite. This reads count objects of type data type from the file in each process. Okay, it's collective across the communicator, and it's very similar to fread or Fortran read. But what you've got here is, if you think about it, every process is calling this. So so if we think about the our standard 2D example, every process will be reading 4 integers, say. But we don't want them to read the same integer. We want process 0 to read the bottom left, process 1 the top left. So how does that happen? Well, that's because there's an intermediate stage where you in MPI, which MPI calls setting the file view, where you've told the IO library which piece of each of the file each process owns. So processes don't all read the same data because the actual position of the read depends on the process's own file view. And it's a similar syntax for write. Apologies, I should probably rewrite these slides to focus on write now that I use them in the context of Bench IO. So how do you set the file view? Well, the way you set the file view is there's a routine called MPI file set view, where you pass the file handle you previously opened, and the first thing is you specify displacement. So you can basically say, which is in bytes, this process wants to start at 100 bytes in, 256 bytes in. So originally, even with just our offset, you can make different processes read different data. However, the important point are the E type and the file type, which you pass in. And so this specifies the starting point in the file. E type is the elementary data type, which is the building block of the file, which would normally be something like MPI double or MPI int. But the important point here is the file type. The file type is the really important parameter here, and this is where you're saying that this process has this view of the file. I only want to see the bottom left-hand corner. You have to pass a data type, which is a subarray, which in 2D could be a vector, but in higher dimensions it would have to be an MPI type subarray. So this is the important thing. Each process specifies its own displacement and file type to say where in the file and what data it's reading. Info again contains hints and system-specific information, but I tend to ignore that and just use MPI info null. Data rep specifies the format of the data in the file. Well, that can be, yeah, I do cover that later. But that I'm not going to go into details of how you do this technically, because it's not, this isn't an MPI course. But what you have to do is you have to specify the displacement and the file type, where this is something like a subarray for this example, to make sure that each process reads different data. So it's very easy to think of it graphically. Once you set a file view, okay, the process only sees the data in the view. So I think of the file view as a mask. So when we do the read, apologies, there's someone at the door and my wife is not well, and I have to, otherwise I'll have to go to the door to answer. I'm really sorry about this. It's just because my wife is not well today. Sorry, yeah, she doesn't feel particularly well. She just tested positive for COVID, so that's the problem. So she can't even answer the door. Sorry about that. Okay, so I've lost my place. When we do the read in our standard example, every process would read, it would just say, I want to read 4 integers. But the reason it gets the right integers is it's got this file view, this mask, and it says the file type is this. It says write one view of the file is just 3, 4, 7, 8. Once you've set a file view with this as the file type, it masks out all the other file. So then you just do linear reads or writes. Okay. So if once you set this file view, this is the only piece of the file you see. And if I write 4 integers, the IO system will automatically say, well, I write to there, 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 and there. I just do MPI file write of 4 integers, but they will go there, 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 and there, because you've set this mask, this file view. Okay, so that's why it's really important. The file views are critical, and you can do this in different ways with different data types, but you want to set a file type for rank 1, which is this thing here, which masks off the whole of the rest of the array. So any reads or writes you do only apply here. And it's up to you to make sure that, for example, for writes, they tally up, that they don't overlap. So the file types should tile the file, as I've said here. So what we're saying is that rank 0 has to specify this file type, rank 1, this one, rank 2, this, rank 3. And so collectively, our file views span the whole file. Sorry, I've got the wrong slide here. Okay. But this, so that seems fairly, obvious, I guess. Now, there was a data, if you go right back, when you did a set view, you specified a data representation. This says, this could be 3 things in MPI-IO. It's a bit weird, native, internal, and external 32. The fastest is native. This just says raw bytes. So some people sometimes ask, what's the file format for MPI-IO? Well, if you specify native, it's just raw data. So if you write 100 double precision numbers, you get a file which is 800 bytes long. There is a portable format called external 32, which will bloat the file slightly, but this allows you to be port readable between different platforms. And so if you are concerned about portability of data formats between two different HPC systems, you could write out as an external 32 and read back in. There's this weird one called internal, which is portability depends on the implementation. I don't really understand what that's for. I would always recommend native. I mean, IO is slow. You just want to get, every time you do IO, your program is not calculating. You just want to get rid of the data. So I would always specify native because it's the fastest. You can measure, if you edit the code, what the difference in speed is between them. But I would say just write native. And then if ever in 2 years' time you're going to a different platform, you can just do a conversion by hand. You can read and write external 32, for example. So this is slightly okay. So I don't know if people are, if you're not familiar with MPI data types, then you can kind of ignore the next couple of slides. But the important point is there are two real ways in MPI to specify this pattern of data. Okay, a block, a gap, and a block. One is with a vector, and one with a subarray. Okay. If you specify it with a vector, you lose the leading gap. And so a vector is element, element, gap, gap, element, element, but it doesn't have the leading gap. That means when you open the file, you have to specify non-zero displacement. So the vector is a pattern, but you have to place it at the correct place in the file. So if you used vectors to describe this pattern, every rank would define the same vector, which is block, gap, but they would use a different displacement to place it at a different place in the file. However, if you use subarrays, if you're familiar with the way that subarrays work, the subarray includes the leading gap. So if you use subarrays, every process specifies a slightly different subarray and uses a zero displacement. So there are lots of possibilities, but if you want to do this kind of pattern in MPI-IO, I would recommend setting the view with subarray types and setting displacement equals 0. Just a technicality for Fortran programmers, because this is a byte offset, it can be bigger than 32 bits, so it has to be you can't store it in an integer. So there's this horrible it has to be an integer of type MPI offset kind. It's rather nasty, but you can also use vectors. Okay, you can use a vector data type, but then you have to specify non-zero displacement, and that is ugly. I don't want the details here, but it is just ugly. Okay, the E type is normally just something like MPI real or MPI float or MPI integer. So that's really just a very high level view of the way that the MPI-IO works. But the important point is that there's this set stage where each process describes which data it owns. In MPI, that's done through derived types, where you could here use vectors or more generally subarrays. And as long as they match up to cover the whole array, then you'll get the right IO pattern. No, because that's a good point, but no, Sean, because MPI offset kind is not a Fortran. In the 2008 interface, then yes, maybe. I'm a bit of an old-fashioned. So I was going to say you can't do that because MPI offset kind is an MPI type, not a Fortran type, but in the 2008 interface, it probably is. So yes, you're probably right. So that slide is, so for historical reasons, well, I don't, for MPI, I tend to teach the sort of older Fortran 90 MPI interface, not the more modern 2008 one, just because it's what most people used to use. But the 2008 one is much, so yes, you probably can do not under MPI offset. That's a good point. I've never done that, but that is a good point. Yeah, that should work. But I'll check. That's a very good point. I'll check that. So yes, if you're using the Fortran 2008 interface, you probably can. So the important point here is that once you've done this, you can do collective I/O. So when you do I/O in almost all the I/O libraries, you can do it collectively or non-collectively. If you specify collective I/O, which in the MPI interface means you stick an underscore all, so if I maybe didn't make that obvious here, but I did MPI file read all, okay? If you do read all or write all, you are guaranteeing that every process is reading and writing, okay? So in that case, the I/O library can be clever, okay? If you call MPI read or write all, okay, the I/O library can say, okay, I know that every process is writing, okay? So I know the yellow process and the blue process are both writing. I know that that means I can gather the data from the yellow process and the blue process into a single block and do a single write. So data aggregation is the key way to getting performance in parallel I/O. And in MPI, that means appending underscore all to your write calls. But what the I/O library can do is, if you did an MPI file write, you get the same answer, but it would have to process every I/O request individually. So it couldn't do this data aggregation. If you do collective I/O, then the I/O library can spot patterns and basically do, and it makes an enormous difference to performance. In fact, there is an exercise to try non-collective I/O for the MPI-IO library. I suspect that will never finish. It's so slow. It can be 100, 1,000 times slower, because what it has to do is it has to basically lock the file, do the I/O, then unlock it. So you really have to. So the important point about parallel I/O is you want to do it collectively. You've described the entire I/O pattern. The I/O library, in principle, knows exactly what every process is going to do, and therefore can analyze the pattern and aggregate things. So instead of doing a large number of small writes, it can do a small number of large writes. Yeah, and I'll come back to that later on. Well, yeah. So what actually happens? What would actually happen is that is probably that I'm in the wrong window here. What the I library probably would do is it would say, okay, I want, what it would do here is it would this is a very simple, but what it would do in principle is it would spot this pattern here, okay? So it would nominate rank 0 as the boss. This is all under the hood, and it would call an MPI gather, and it would gather all this data together. So actually there is synchronization, but it actually happens. It's because this data rearrangement is done through collective MPI collectives like gathers and all gathers and such like. So yes, all the synchronization point, the appropriate synchronization will be put in for you by all the collective I/O operations, but they kind of happen for free because the data aggregation is done through standard MPI collectors. Like you could imagine that they'd all do an MPI gather, for example. Does that make sense? There's a lot of data movement going on here. Yeah. So again, you can pass all these calls take info objects, which are standard MPI things, which are key value pairs. So you do have a slight quandary here, paradox, I guess, that I said before that different I/O systems, different parallel file systems, different I/O libraries, different parallel file systems will have different options to them, lots of configuration options. So, you know, if you're using, as I said, there was an IBM system called GPFS, I think it's now called SpectraScale or something. It would have different options, different terminologies for striping and such like than Lustre does. However, you want MPI to be portable. So how can you have a portable interface that allows you to have system-specific options? Well, they have this catch-all thing called an info object, which you can set with key value pairs. But if the runtime library doesn't recognize them, it just ignores them. So in some sense, it's portable because they can be ignored. So one way of doing I/O program, parallel I/O, is to set these inflow objects to specify things like buffer sizes, stripe counts. But to be honest, I think it's much easier to write very naive MPI-IO, and it's much easier to tune the Lustre file system with these command line commands than to use MPI-IO hints. That's just my observation. So this is a slightly of a run through, but the MPI-IO calls is deceptively simple. You have a file open, file read or write, file close. But the important point is in between the open and the read or write, you do this MPI file set view. So the user must define appropriate file types if the file view is correct in each process. And this is the difficult part. And if you told me, can I do unstructured parallel IO and MPI-IO? I said yes, as long as you can find a derived type, an MPI derived type that describes the distribution of the data, then you can do that IO pattern in MPI-IO. But really, the important point is use collective calls whenever you can. That's IO collectives. That in an MPI, that means read all, write all. But other libraries have their own way of specifying that, because it enables the IO library to merge reads and writes, enables a smaller number of larger IO operations from or to disk, and that is an absolutely critical step. It makes enormous differences to the performance. So that was a bit of a run through, but hopefully, I think the main point is to understand the MPI-IO model, which is open the file, set a file view, then do reads and writes. And the important point is that once you set the file view, you only see you mask off all the other data, and you can just do linear reads and writes. So the next thing to do is just to do the exercise. I've lost the exercise. It's closed itself. I'll just sorry, can you still hear me? I had a slight glitch there. My machine glitched for a second. Can people still hear me? Did you? Yes, right. Okay, I don't know what happened. Maybe it was just the internet. Yeah, okay, fine, thanks. I had a very, so it was very strange. So just to basically recap what we're doing. Sorry, I have too many windows open and I get lost because my brain can't cope. Sorry about this. I've lost the window I need to show you. Okay. Right. So what we're going to do now is we'll have a practical, then lunch. But after lunch, I'll talk about how you configure the Lustre file system, and this is talking about you setting the striping and such like. But the original exercise is just to run parallel IO and look at the MPI-IO performance, and I want the exercise is so you can carry on where you left off. Yes, you are seeing this. But we've got some feeling now that, in principle, a process can do about 3/4 of a gigabyte a second. A node can do about 15 gigabytes per second. What are we going to get with MPI-IO? And I would start off doing this. So the idea of the MPI-IO is to start off with one node and task per node equals 128. And if you do this bench IO 128, 128 local MPI-IO, that does parallel IO, but it does it to the three stripings. It does it to the unstriped, the stripes, and the full stripes. And the question is, do we see, does MPI-IO benefit from striping? Okay. So we've got some data here, have we? Okay. So and how many nodes was that? Okay, so right, so we can come back to, so these are interesting. Okay, so so I'll recap these numbers after lunch, but it's the performance of MPI-IO is slightly counterintuitive, and those numbers are exactly what I expect. You want to try more nodes, but they're interesting, but try them on more nodes. But you'll see that, okay, so you'll see that you are benefiting from striping, not a huge amount. You should benefit more on more nodes, okay? But that is even interesting on one node. So as I said, MPI performance, now try 2, 4. You can actually go up to more than 8 nodes. You can actually go up to, so you could try non-collective, but that'll be really slow. And you can try a few things. But I think this is really just getting the scalability on. So I think the two things to do would be to look at that, and it'll be interesting to try it on the NVMe file system as well. I say 8 nodes here as a maximum, but in fact, you should be able to, let's have a look. If I can share. I think it's S account, S control, show res, I think. Whoops. Reservation. There we are. So we're running in this reservation here, which is 4,096 processes, 16 nodes, right? So you'll be able to go up to 16. So I said in the sheet that only go up to 8, but you should be actually going up to 16 is interesting because it's more than 12. So 12 is the number of OSTs and 16 is, so actually going up to 16 nodes will be interesting. I don't want to jump ahead, but by default, the MPI-IO performance is relatively disappointing, and we'll discuss why that is after the break. But it's interesting to get these numbers actually. So it would be interesting to run on. You can run up to 16 nodes on this. Yeah, 16 nodes you can run on. So there was nice results. That was from Lokesh. So is there about 3? That's fine. But yeah, feel free to go up to 16 nodes. More than 16 nodes won't run in the reservation. You could run that outside the reservation, but within the reservation, you won't be able to run up to 16. You'll only be able to run up to 16. Okay, so are there any questions on that? I think, I mean, we'll have a, hopefully that should run out the box, and we can discuss. We'll spend some time after lunch discussing the results, because the results are understandable, maybe, but not optimal. Maybe not what you'd hope. Okay. So I will, and it's all to do with the way that MPI-IO optimizes. It's all to do with the way that MPI-IO utilizes the Lustre file system. Yeah. Okay, so you're getting benefits from multiple nodes. That's very interesting. So you see, one node full stripe was 1.2, 2 nodes full stripe. You'd hope was twice as much, but it's 1.9. So they're very interesting actually. We can discuss these, and if you get more, that'd be really good. But yeah, they're as I'd expect, and they're They're not 2 gigabytes per second, not brilliant, but we are at least scaling. So it'd be really interesting if somebody could get numbers up to 16 nodes, and we can look at those. So I will stop sharing my just check his okay. I will stop sharing my screen. So it'd be useful if people will start. They are very interesting results people are showing already. So I'll be around for the next 15 minutes if you have any questions or problems running. But then, as I said, the practical session until 1, lunch for an hour, not provided, and then we'll start the next session at 2 o'clock. But we'll definitely recap the MPI-IO practicals. Already the numbers that people are showing look very interesting.